Physicists say that the universe had its start in an event known as the Big Bang, generally 13.7 billion years ago. This event marks the beginning of all that we know in the universe, an extraordinary explosion that led to all matter, energy, and existence itself. The theory of how things came to be has long been the predominant scientific explanation for the start and evolution of the universe, describing a moment when the universe rapidly expanded from a hot, dense state into the vast universe we observe today. However, while this theory offers a framework for understanding the universe's early development, it leaves many questions unanswered. One of the most captivating questions is what triggered this immense explosion. If the Big Bang was the start of everything, what caused it and why did it occur? These are questions that have fueled the curiosity of scientists for many years, leading to intense study, discussion, and observation in the quest to understand the origins of our universe. Over time, researchers have continued to explore and study both the science and history of our universe. The Big Bang Theory has been the most dominant explanation for everything we see, from the distribution of galaxies to the cosmic microwave background radiation, the faint glow of the Big Bang itself. Countless studies have been conducted over the years, with thousands of scientists around the world dedicating their careers to uncovering the mysteries of the universe. The data gathered from these studies has consistently supported the theory of how things came to be as the leading model for the evolution of the universe. According to the theory, a mysterious force known as dark energy plays a pivotal role in the ongoing expansion of the universe. Dark energy, which is believed to be far more abundant than the energy found within galaxies, acts as a repulsive force that causes the universe to expand at an accelerating rate, opposing the gravitational forces that would normally pull everything back together. The field of cosmology has advanced significantly over time as technology progresses, and we develop new tools for observation and experimentation. Our understanding of the universe continues to evolve, and many things we once accepted as absolute truths have been shown to be incomplete or even entirely wrong as new evidence becomes available. A prominent figure in modern theoretical physics, Michio Kaku, has pointed out that even the theory of the universe's origins, long considered the foundation of cosmology, is now facing challenges. Recently, observations made by the James Webb Space Telescope have sparked significant debate among scientists. The telescope has identified 750 new galaxies that appear vastly different from what was previously predicted based on past models. These startling discoveries are compelling researchers to reconsider established theories and delve deeper into the mysteries of the universe. As these revelations unfold, they hold the potential to reshape our understanding of the cosmos. The James Webb Space Telescope, with its cutting-edge technology, is changing the way we view the universe. The findings it has made so far have pushed the boundaries of our knowledge, particularly regarding the formation and development of galaxies. The telescope has captured images of many galaxies that challenge previous assumptions, leading to a new perspective on the universe's evolution. These discoveries are exciting not only because of what they reveal, but also because they challenge long-held beliefs about the Big Bang. For those eager to stay informed about the latest advances in astronomy and cosmology, the images and data coming from the James Webb Space Telescope offer a fascinating glimpse into the farthest reaches of space. The newly discovered galaxies, with their stunning structures and astounding numbers, are prompting researchers to revisit their theories and explore new possibilities regarding the universe's beginnings. The James Webb Space Telescope has delivered some of the most breathtaking images of galaxies ever captured. In a single image, one can see countless galaxies grouped together, their beauty and enormity surprising to the average person. However, for professionals and experts, these images are not just visually striking, they are also profoundly astonishing. The galaxies captured by the telescope are vastly different from what scientists had expected based on the Big Bang model. They appear smaller, more diverse, and surprisingly old, raising questions about the accuracy of existing cosmological theories. These surprising observations are generating waves of concern within the scientific community, with some analysts even using the word panic to describe the reactions to these new findings. The discrepancies between what was previously expected and what has been observed are driving scientists to re-examine the fundamental assumptions of the Big Bang Theory. For years, the theory of how things came to be has served as the primary explanation for the origins of the universe. According to this theory, approximately 13.7 billion years ago, the universe began as a single unimaginably hot, dense point that rapidly expanded in what is commonly referred to as the Big Bang. This explosive event set into motion the evolution of the universe, ultimately leading to the formation of galaxies, stars, and planets, including our own. However, the new images captured by the James Webb Space Telescope have cast doubt on this long-accepted story. These images challenge the established narrative of the universe's beginning and have opened the door to further possibilities regarding how the universe came to be. The galaxies revealed in these images appear to be too small, smooth, and old to fit within the framework of the Big Bang Theory, suggesting that the true story of the universe's origins might be far more complex than previously thought. One of the most striking aspects of the universe, as seen by the James Webb Space Telescope, is the size of these galaxies. These galaxies are several times smaller than those captured by the Hubble Space Telescope, which directly contradicts the assumptions of the Big Bang Theory. According to this theory, as the universe expands, objects within it should appear larger as the distance between them increases. However, the galaxies observed by the James Webb Telescope are not behaving as expected. They are smaller and more compact, defying the standard model of cosmic evolution. Additionally, the smoothness of these galaxies is a surprising and puzzling feature. The Big Bang Theory predicts that galaxies should show a significant degree of irregularity in their shapes, with noticeable variations due to the tumultuous processes of their formation and evolution. However, these new galaxies are remarkably smooth, with far less complexity than scientists would expect for galaxies of their age. This smoothness challenges the timeline of galaxy development and suggests that something about the standard model may need to be rethought. At the beginning of the universe, all matter, energy, and the building blocks of the universe were packed into a single point of unimaginable density, known as a singularity. This singularity represents the starting point of everything, where the laws of physics as we understand them begin to break down.
In this state, matter and energy were so densely packed that their behavior becomes difficult to describe using conventional physics. The nature of the singularity is rooted in Albert Einstein's theory of general relativity, which explains how gravity acts on massive objects within it. The density of matter reached an infinitely high value, creating conditions that we cannot fully comprehend or replicate with our current understanding of physics. The temperature at this time was extreme, far exceeding anything observable in the universe today. It is within the singularity that the seeds of the universe were planted, with all the mass and energy needed to create everything we see around us today. After the initial singularity, the universe began to expand and swell, going through a rapid process that stretched the fabric of space itself. This expansion, known as cosmic inflation, occurred at an incredible rate, far exceeding the speed of light. During this phase, the universe expanded drastically, smoothing out any irregularities and laying the foundation for the large-scale structures that would later form, such as galaxies and stars. Cosmic inflation played a crucial role in shaping the universe as we know it today. It homogenized the distribution of matter and energy, ensuring that the universe would be relatively uniform on a large scale. As the universe continued to expand, the rate of expansion gradually slowed, leading to the development of more complex structures. Scientists have been able to observe the effects of this ongoing expansion through phenomena like the redshift of light from distant galaxies, which shows how the universe continues to grow and evolve over time. During the early stages of the universe's development, all matter was compressed into a small volume, creating conditions that would have made it impossible for stable matter to exist in its current form. However, as the universe expanded and cooled, these extreme conditions began to change, allowing particles like protons, neutrons, and electrons to form. These particles interacted with the surrounding light and energy, eventually leading to the creation of matter as we know it. This process, known as nucleosynthesis, occurred during the first few minutes after the Big Bang and played a critical role in the creation of the elements that make up our universe. Interestingly, while scientists expected to see chaotic and disturbed galaxies due to various impacts during this early period, the images captured by the James Webb Space Telescope tell a different story. Instead of observing tumultuous galaxies, the telescope has revealed well-organized spiral and elliptical patterns that resemble the galaxies we see in the universe today. This challenges the idea that collisions and impacts were common in the early universe. The illusion predicted by the expanding universe theory, in which objects should appear smaller due to cosmic expansion, also fails to hold up against these powerful observations. The galaxies captured by the James Webb Telescope do not appear minuscule, raising further questions about the validity of the Big Bang theory. Additionally, the age and abundance of these galaxies challenged the idea that the universe followed a predictable path of development and evolution. The telescope's infrared capabilities allow it to focus on the light from distant galaxies, providing insights into the ages of stars and galaxies. This has led to the discovery that many of these newly found galaxies are much older than scientists had anticipated, further complicating the narrative of cosmic history. As we continue to learn more from the James Webb Space Telescope, it becomes increasingly clear that our understanding of the universe may need to be revised. The potential implications of the telescope's discoveries extend beyond re-examining the Big Bang theory. One significant aspect of this challenge is the role of dark matter and dark energy in shaping the universe's development. Dark matter, which interacts with gravity but not with light, remains largely invisible, making it difficult to study directly. However, its effects on the structure of galaxies and the expansion of the universe are undeniable. Similarly, dark energy is thought to be responsible for the accelerated expansion of the universe, but its true nature remains elusive. In conclusion, the groundbreaking findings of the James Webb Space Telescope have cast doubt on the validity of the Big Bang theory. The surprising images of small, smooth, and old galaxies challenge our existing understanding of the universe's origins. While the Big Bang theory remains the leading explanation for cosmic evolution, these new discoveries highlight the need for a more nuanced and flexible understanding of the universe's beginnings. The future of cosmology may involve a reevaluation of our assumptions about the universe's formation, the role of dark matter and energy, and the nature of the Big Bang itself. As new data continues to emerge from the James Webb Space Telescope and other cutting-edge tools, we are likely to see even more radical shifts in our understanding of the cosmos. The discoveries made by the James Webb Space Telescope have revolutionized our understanding of the cosmos, prompting new questions and hypotheses. One of the most intriguing aspects of the telescope's findings is the unexpected nature of the galaxies it has observed. These newly discovered galaxies challenge some of the most fundamental assumptions of cosmology, particularly regarding their size, smoothness, and age. They appear more mature and organized than was previously thought to be possible so early in the universe's history. The Big Bang theory, which has long been the cornerstone of cosmology, suggests that the universe began in a singular event, rapidly expanding from a dense, hot state. This expansion is believed to have led to the gradual formation of galaxies, stars, and other cosmic structures. However, the early images from the James Webb Space Telescope show galaxies that do not conform to the expected patterns. These galaxies are not as chaotic or irregular as was predicted by models of the universe's infancy. Instead, they exhibit surprisingly well-defined shapes, challenging the notion that the universe's early evolution was disorderly. These anomalies suggest that the process of galaxy formation may be far more complex than previously assumed. Some researchers speculate that these galaxies may be remnants of an earlier epoch of cosmic history that could offer new insights into the early universe. The question arises whether they formed in a different manner or whether they could be the product of more recent cosmic events that have yet to be fully understood. Another important question raised by the findings of the James Webb Space Telescope is the potential role of alternative forces or processes in shaping the early universe. For instance, the impact of dark matter and dark energy on galaxy formation could be much more significant than originally thought. These forces, though largely invisible, are known to exert substantial influence over large cosmic structures. Dark matter, for instance, is believed to make up a large percentage of the universe's mass, yet it does not interact with light, making it nearly impossible to observe directly. This presence is inferred based on its gravitational effects on visible matter.
Similarly, dark energy, thought to be responsible for the accelerated expansion of the universe, may play a more significant role in the early stages of cosmic evolution than the current models suggest. Additionally, these new findings are prompting a reevaluation of our understanding of cosmic inflation. While the rapid expansion of the universe during the first moments after the Big Bang has been widely accepted, the details of how this inflation occurred and how it might have influenced the formation of structures in the early universe remain unclear. As scientists gather more data, they are beginning to realize that inflation could have taken place in a more complex and varied manner than previously thought. This could mean that inflation itself may have been responsible for some of the surprising features observed in the newly discovered galaxies. The surprises from the James Webb Space Telescope are not only reshaping how we view the universe's past, but are also pushing the boundaries of what is scientifically possible. The implications of these findings extend far beyond the Big Bang theory, forcing a reconsideration of established cosmological models and encouraging the scientific community to explore new theories that account for these unexpected observations. The next few years promise to be a thrilling period of discovery as researchers work to piece together the true history of the universe using the revolutionary data gathered by the James Webb Space Telescope.